Okay, great. Let's start. Hi, everyone. This is Charlie. I'm the co-founder and the CEO of XCamp. Today, we have the 2023-2024 USACO season live solution for the zero level. We have Arvind here. He is our teacher. Also, he is the ICPC World Finalist. ICPC is the college level contest. Um, yeah, we are very happy to have him. He has a lot of experience, also not only on the contest but also teaching and communications with the students. Arvin, now I turn the screen to you.
Yeah, hello. Yeah, I'm Arvind. Um, yeah. Do we want to start with the solutions or how do we? Okay. Yeah. Okay. Yeah, I can share my screen. Yeah. So let's go through. Wait, wrong. Yeah, that's correct. Yeah. So let's go through the solutions of the three problems. Yeah, so let's look at the first problem. So basically, yeah, so there are N cows that are being interviewed for a position, and each one has a competency score CI ranging from 1 to C inclusive. And you're given the values of CI, and some of them are equal to 0, which means that they haven't been assigned yet. And you're also given Q pairs, AJ to HJ. And basically what this means is that if you consider the prefix max from 1 to HJ, then, sorry, 1 to AJ, then HJ is the first place that's greater than the prefix max. And it's basically asking you to fill in the zeros that's lexicographically smallest that satisfies all these AJ, HJ constraints. Um, and yeah, just a remark. Yeah, so I think this problem is definitely the trickiest one this contest, but let's go through the problem. Yeah. So one thing you can think about is so basically for each AJ HJ pair, you can consider the interval AJ plus 1 to HJ. So just consider like all these kinds of LR intervals that are uh, of the form AJ plus 1 to HJ. And let's try to see what kinds of properties they have. So what we know about an interval is basically if we consider the prefix max m, all these elements have to be less than or equal to m, and then this has to be strictly greater than m. This is because this is the first element that is strictly greater than the prefix max. So let's try looking at some properties of these intervals. So let's say that the intervals intersect. So if they share the same right endpoint, then basically we have that if this is the prefix max, then uh yeah, uh, yeah. So basically this is the first element. If this is M1 and this is M2, this is the first element that's greater than M2, and this is the first element that's greater than M1. But since we have this interval here, all of these elements have to be less than or equal to M1. So this tells you that um, if you have two intervals that share the same right endpoint, then we can just eliminate this interval and just take the bigger one. So one thing is if intervals share right endpoint, take the bigger one. And let's consider another case in which the intervals intersect. So let's say I have two intervals that intersect and they don't have the same right endpoints, right? So if this is a prefix maximum m, then this is the first element here that's greater than m, and all of these elements are less than or equal to m. So this tells you that this element is less than or equal to m. And then, so let's just say this is m2, like this prefix, yeah. So prefix max here is is m2, which is less than or equal to m. And this is the first element that's greater than m2. But that's a contradiction, right? Because this here was supposed to be the first element that was greater than m2. So basically, you're not allowed to have intersections like this. So basically, uh, if right endpoints are different, then there's no solution. So because of property 2, that means that all of the intervals, they're only allowed to share the right endpoint. And because of property 1, we can always take the longest interval. So this basically tells us that we can assume the intervals are disjoint. So now let's look at what we can say given the intervals are disjoint. Yeah, just a reminder, each interval represents like aj plus 1 to hj. Yeah, so let's just consider disjoint intervals, right? Um, and basically we can consider going from left to right, and then this has to be greater than the prefix max here, and this has to be less than or equal to the prefix max here. But we know that this, since it's the right endpoint of an interval, this is the greatest element within its prefix. So we can actually reduce the problem to this size, right? And what we can do is some of these values will equal 0, and we can greedily change some of them. We can greedily change them to 1s, and then yeah, and then you'll have like some non-zeros in your input already. So this might be like 2, 3, 5, 7 or something. And this has to be greater than 7, right? So one thing that you need to have is that this is the first element that is greater than everything else to the left, right? Um, so basically, uh, all these yeah, all these elements have to be greater than or equal to the second largest in this range, right? So if there exists an element in this range that's greater than or equal to the second largest in this range, then we're done. Otherwise, since we want to find the lexicographically smallest, you have to look left to the closest 0 and then change this to be the second largest. Yeah, so just to repeat, since this is the first element, since this is the first element that's greater than this prefix max, then that means everything to the left, uh, or the prefix max of the left should be at least the second largest in the interval. So if there's no element here that's at least the second largest, then we have to replace some element with some element that's at least the second largest. And since we're looking for lexicographically smallest, we pick the closest 0 to the left and replace it with the second largest. And since this is the largest in its prefix, then we don't care about any of the elements to the left. So we're only reducing the problem to this region in red. Yeah. And then we'll set this thing equal to, if it's not already set, you can set this equal to max. So if this is L and this is R, then you can set this equal to max C from 1 to R minus 1 plus 1, since this has to be greater than everything to its left. But if there's a 0, and let's say that there's no zeros here, and we're processing the next interval, and we want to replace a zero to the left with the second maximum. So we also have to add some kind of, we also consider this as a candidate for the zero. And if this is not as large as the second maximum, then you can consider this as a candidate to increment to the second largest. Um, yeah, so that's essentially the idea. So let me summarize this, or let me summarize the idea. So basically, we can reduce the problem to something where the intervals are all disjoint, and then we can process the intervals one by one. And within each interval, you can greedily set the zeros equal to 1. And we must have, we argued earlier that uh, we must have that the prefix max to the left must be at least the second largest element. And since we want the lexicographically smallest, you find the closest zero to your left and change that to the second smallest. And then you change this to max plus 1. And if it's a zero, you can still consider it as a candidate for an element to change when you're looking at the next interval. And then at the end, just change all the zeros to ones and then check if it's valid. Yeah. So that's the idea for solution to problem 1. Yeah, so there's a lot of greedy arguments that are made in this. And I think reducing the problem to just focus on this range from the rightmost endpoint of the previous interval to the rightmost endpoint of the current interval is important. Yeah. Any questions? Yeah, and you can like during implementation, you might want to pre-compute things like closest zero to the left an element. Yeah, and then uh, just process these kinds of ranges in blocks one by one and solve for each block. Yeah. Yeah, I'll move on to the next problem. Yeah, so I believe this was the most challenging problem in the contest. So this problem is called potion farming. So basically, yeah, so there's there's a series of n rooms that are connected by n minus 1 edges. So it's basically a tree. Yeah, and then you can think of the tree rooted as at 1, and you can explore the map by making a series of traversals. So um, you start the traversal from room 1, and you go to any other room, and the map is complete once um, every room is visited by at least one traversal. And the main goal is to complete the map and the minimum number of traversals. So I'll get to the rest of the problem, but part of the problem is finding the minimum number of traversals. So let's just discuss that first. Yeah, and you have, uh, yeah, so for your constraints, I'll explain the rest of the problem later, but you have n is at most 10 to the 5, and basically from the root, you want to explore everything in the minimum number of traversals. So a few observations. So let's say a traversal starts from the root to some vertex u. So one observation is uh, it doesn't worsen your answer if you keep traversing. So basically, you can keep traversing until it reach a leaf, until you hit the leaf. Observations. Um, and then basically, yeah, so each traversal, is basically if you hit the same leaf, it's kind of a waste. So you want to hit a different leaf each time. So this implies that number of traversals is equal to the number of leaves. So basically, given your tree and there's a bunch of leaves, each traversal, it's optimal to end at a leaf. So the total number of traversals is going to equal the total number of leaves, right? So yeah, so part of the problem is like knowing like what the minimum number of traversals looks like. So let's continue reading the problem. So your secondary goal is to farm as many potions as possible. So before a traversal begins, a potion will spawn at some room in the map. You can pick up the potion by visiting the room that the potion spawned in at the current traversal. And if you don't pick up the potion, then it'll disappear. So given the minimum number of traversals, uh, you want to collect the maximum number of potions, right? Um, yeah. Uh, yeah. So basically, like you know that you'll finish in T traversals. So consider where the potions will be from times 1 to up to T, right? And you know what the optimal traversals for those optimal paths for the T traversals is? It's just paths to the leaf. Um, so basically you want to order these traversals so that um yeah, so that you hit the potion at each traversal. So basically like from times 1 through T, there'll be a potion at a different location, and you want to maximize the number of traversals that'll pass through that potion, right? So basically, uh, if you start from the root and a traversal goes to the leaf, then you're going to hit the potion if it's in the path to that leaf, right? So basically, yeah. So basically, you reach a potion uh, if this leaf is in the subtree of that potion, right? So basically, you want to match potions to leaves. So this problem reduces to matching potions to leaves. Yeah. And you can argue that it's best, yeah. So let's just say we have like a leaf here, and there's two potions that are on the path to the leaf. Uh, it's always better to match the lower potion to the leaf, than the higher potion to the leaf. Because if you match the higher potion to the leaf, um, uh, either you match the yeah. So either yeah. So basically, you either you match the lower potion to a different leaf, in which case you can get a similar solution and doing this. So there's something in greedy algorithms called exchange arguments. Basically, if you swap something in a suboptimal solution and things will only get better, then that's how to show something is optimal. So basically, suppose that the one at the top was matched to the leaf. If you swap, and if you suppose the one at the bottom is matched to a different leaf, then if you swap them, the solution won't get worse. Um, and I guess the other case is where the one at the top, uh, the one at the top is matched to a leaf, and this is matched to nothing. Then if you swap, then you can match this to the leaf, and you have more options to match to the top too. So you could potentially get +1, right? So the optimal strategy uh, is to match uh, lowest potion to leaf, right? So basically what we want to do is um, like one way we can do this is iterate through potions that are from deepest in the tree to highest in the tree. from lowest to highest. And then, yeah, so when you're at your potion, just match to any leaf in the subtree. Yeah, so this will be like naively, if you just iterate over the potions that are from lowest to highest, and then match to any leaf in the subtree. So you're iterating over like O of n potions, and then the time to find a leaf, which is like a depth first search, will be O of n. So this will be O of n squared. So you can pass the subtasks using this. I think there's, yeah. So it's like this n less than or equal to 1000 subtask. Um, but we can do better. So the idea is you can do this recursively. So you want to solve for a vertex, and then you match the potions in its subtrees to their leaves. So basically you recurse over all these and you match their potions to their leaves. And once you recurse, you keep track of the number of remaining leaves. Yeah, so basically you can solve for this subtree since we know it's optimal to match the deeper potions uh before the higher positions, and just match these to their leaves, and then go up the sub when you're and then you can return the number of leaves that are remaining. So you can do something like int solve int u for the child um uh, num leaves plus equals solve v, and then yeah, so if and then match the potions from u, and then you might need to decrease num leaves based on if there's potions at u, and then you return num leaves. Yeah, so the idea is you can match the potions from lowest to highest. And we can do this recursively by matching the potion in each subtree to leaves. And you can recursively find the number of leaves if you optimally match the subtrees. And then if there are potions that are at location U, then you can match these to any arbitrary leaves. And then like decrement num leaves, depending on how many potions you match, and you return num leaves. Yeah, so let me summarize. Yeah, so you can find the minimum number of traversals because each traversal will hit a leaf. So it's going to be the number of leaves. Um, and then the problem reduces to matching the potions to the leaves. Um, and we can show the optimal strategy is to match the lower potions first. Uh, and since it's optimal to match the lowest potions first, then we can solve this recursively where we match all the potions in our subtrees. And then we get the number of remaining available leaves and then match our potions to those leaves. Yeah, so that's the solution to problem 2. Yeah, any questions? I'll go to problem 3. Yeah, I guess, yeah, they're equivalent. Okay, let's go to this problem. Yeah, so Bessie, there's n months, each with A1 to AN days, respectively. And there's also weeks where each week is L days, with L being a positive integer. Um, yeah, so there's some conditions on the number of weeks that we can have. Um, So each month is at least 4 weeks long. So basically each AI is at least 4 times L. And then yeah, for the correct L, there are at most 3 distinct values of AI mod L. Yeah. Um, yeah. Okay. Yeah. So yeah. So and it's asking you to find the sum of all the possible values of L. Um, yeah. So I guess in this case, these are the months. They're around 30. Yeah. And then you can show that these are possible values of L because for L equals 7, each month is 0, 2, or 3 mod L. Yeah. And then the constraints for here is AI is at most 4 times 10 to the 9. And then the subtask is like uh, AI is at most 10 to the 6th. Yeah. Um, yeah. And then also N is at most 10 to the 4th. Yeah. Uh, yeah. So let's see what's true. Like, let's see what conditions might hold if a particular L works, right? Um, so let's see what conditions are true for a valid L. Okay. Um, so we know that there has to be at most 3 distinct values mod L, right? Um, so basically, like one thing that we know if 2 things are equivalent mod L, basically, um, like like if AI and yeah, so basically there's 3 distinct values mod L. Let's say they're like C1, C2, C3. And then if AI is equal to C1 and then AJ is equal to C1 mod L, that basically gives us that um, L divides AI minus AJ, right? So basically, uh, yeah, if any two things are the same mod L, then that means L divides AI minus AJ. So just consider this some kind of graph, right? Yeah. So consider a graph. Uh, of course, given the constraints, yeah, so we can't like construct this graph for every L. But let's say that there's a graph where there's an edge from U to V if L divides their difference. So edge from U to V if L divides AU minus AV, right? Um, so what can we observe about this graph? So basically, uh, for everything that's if these are your distinct values, for example, for everything that's equivalent to C1 mod L, they're going to form a connected component, right? Because L can yeah, L can divide the difference if they have the same residue mod L, right? So if we construct this kind of graph where there's an edge from U to V, if L divides the difference of the elements, then that means there's going to be at most 3 connected components, right? Um, yeah. Oh yeah, one more thing. Yeah, just assume the values of AI are distinct. If there's duplicates, it doesn't matter. Um, or we can just reduce it so it's distinct. Yeah. So if there's an edge from U to V, if L divides AU minus AV, since there's at most 3 distinct values mod L, then there's at most 3 connected components. So there's something called a pigeonhole principle. If like if you have like if you have like yeah, you might have heard of this. If you have like k minus one pigeons in k holes, then there exists a hole with more than one pigeon. So if you just consider the first four elements, A1, uh, A2, A3, A4, and you assume they're distinct, then this will be in some component, C1, C2. So there's up to three components, right? C3 and C4. And there exists two elements that are in the same component. So, right? There exists two elements that are in the same component, right? So for any L, if you just consider the first four elements, there exists two elements that are in the same component. So basically for any L, like there exists two elements among the first four that it divides. So for any L, um, L divides AI minus AJ for 1 less than or equal to I less than J less than or equal to 4, right? Um, so we can use this as a way to consider our candidates for L. So basically candidates for L is like divisors of um, AI minus AJ, where 1 less than or equal to I less than J less than or equal to 4. So basically, number of ways to pick this IJ pairs is like 4 choose 2. So six numbers. So basically there's six ways to pair them, and L has to be a divisor of one of these pairs. And we have from the constraints that um, it's up to 4 times 10 to the 9. So basically we can uh, just iterate over the divisors. So um, basically number of candidates for L is like most like square root 4 times 10 to the 9 um yeah times 6 uh yeah, I think you can show something stronger, but the idea is that there's not that many candidates for L, so then you can just do brute force to check if L is valid. Yeah, so to check if L is valid, yeah. Yeah, so to check if L is valid, you can find the remainder of L modulo all the AIs from A1 to AN. And if you get at most three distinct values, then that's a valid L. Yeah. I think, yeah, you can probably show something stronger, like this to the power of 1/3, but it's just a weak bound. But yeah, you can, yeah, so the number of candidates for L is small. I'll just summarize the idea again. Um, since there's three distinct values, mod L, you can construct a graph, or just like not explicitly construct it, but just consider the graph where there's an edge from U to V if L divides AU minus AV. And if you consider the first four elements, then by the pigeonhole principle, you know that two of them must lie in the same component. So that means L must divide AI minus AJ uh, for some ij. So, and since we only have four elements, then there's six candidates for AI minus AJ, and you just find the divisors of all these AI minus AJs. Um, and this gives you a small number of candidates for L, and you can brute force um, to check if L is valid and compute the sum from there. Yeah. Any questions? Yeah, so that's the solution for problem 3. Yeah, so yeah, probably like problem 2 is more of a standard problem, and problem 3, yeah, you need to make some observations. Yeah, it's a bit tricky, but um, yeah, but coming up with it is a bit tricky. And then problem 1 is, uh, yeah, problem 1 Yeah. Problem 1 was probably the trickiest one. Yeah, it'll be on YouTube. Yeah. Yeah, I guess for problem 1, like this task for input 3 is doable. Um, yeah, like like you can get free points with brute force. Um, yeah, yeah, yeah. That's it for my solutions for the silver. But yeah, any questions?
Yeah, here, Arvin, yeah, here the summary page. Maybe you can use these slides to give a quick summary.
Yeah, so for competency, which I think was the most tricky problem, there were a lot of like greedy arguments that we made, like certain arguments about the structure of the intervals, like looking at the optimal solution, and then certain arguments about what elements we need to place to give the lexicographically smallest solution. Yeah, so this was a greedy problem. And then potion farming was maybe more of a standard problem, but it was a tree problem. And you have to make use some greedy arguments to uh, argue that you want to match the lower potions first. Um, and then yeah, and then and then a way to implement this efficiently was with using recursion or DFS. Yeah, and then calendar was a number theory problem. And then yeah, and then also requires like some observation using pigeonhole principle. But yeah, um, well, yeah, about cutoff estimates, I'm not really sure, but I personally thought uh, problem 1 was definitely hard for a silver problem, and then problem 2 was probably standard, maybe on the easier end, and then problem 3, um, um, hard to say. Maybe the observation is like kind of clever, but I don't think it was like extremely hard for silver.
Thank you, Arvin. Do you see any more questions in the chat we need to
I think
answer?
some people are asking where they can see the recording or like a link of the YouTube.
Yes, we have a YouTube live. If you just search XCamp live, server live, you will see this recording. Yeah. Okay, great. Also, you can see for each problem, we have classes to teach this knowledge and the practices. You know, we have different 200 level, 300 level, 400 level. Also, more importantly, we have mock test class. I think some of you might already noticed, you know, you may know the knowledge, but when you work on the problem, especially during the contest time, it's pretty challenging. So mock test is necessary to achieve a higher score, especially within a time limit. Okay, great. We provide another service called the USACO report card. So please go to our website, xcamp.org or xcamp.academy. You will see the USACO report button. Just click that and submit your test cases. So based on that, we will compute your estimated score. Also, we will give you an analytic report. So we will see which part you are kind of short of, which part you might need to put more efforts. So yes, please go to our website and submit your report. We will submit your score, so we will send you a report in 12 hours. It is here, yeah. Great. I think we have these QA sessions. In addition, we have classes from year-round weekend class. Every year we have 4 quarters. Each quarter we have 10-week class. Also, we have on-site camps. We have winter camp and the summer camp. The summer camp is coming for 2 weeks, from July 22nd to August 2nd. Also, we have a mock test class, as just mentioned. Every week, we have 4-hour mock test. For the Grandmaster class, it's for the gold and the platinum level. You might not be there yet, but pretty soon you might join our Grandmaster class. In addition, if you are interested in ABCSA help, we have series classes. Okay, that's all for today. Thank you very much again, Arvind. Thank you for your explanation. Thank you for your help. Also for the students, thank you for your coming. Hope you get a good score. If not, it's okay. You may try next time. This is a learning process. Learning is more important than just achieve a score. Hope you enjoy this journey. Okay, thank you all. Have a nice good night. Okay, somebody asked me the YouTube recording. Yes, let me share you the YouTube link. Okay, give me 1 second. Let me share that with you. The YouTube link. Yeah. Here's the YouTube link. Okay, yeah. Thank you, Arvind. Talk later.
Yeah, thank you.
Thank
Bye.
you.